which will be given by Jerry Sanders. So take it away.
Okay, can you hear me?
Yep.
Okay, I'm going to talk very briefly about ISRU and how we look at dust and regolith. Talk a little bit about the knowledge gaps that still exist and the challenges and where we see ourselves going. So next chart. From a very top level perspective, the ISRU activities cover everything from prospect to product in the end. And includes initially resource assessment, starting from the global perspective down to the local on-site perspective. From a consumable production perspective, we are looking at two pathways: what we can get out of the bulk regolith, oxygen and metals. The other pathway is looking forward towards the water and other volatiles that hopefully exist in mineable quantities in the permanently shadowed craters. At the same time, to support both of those activities, as well as surface infrastructure and human activities, we look at surface construction and manufacturing activities, such as landing pads, berms, and such, leading to consumable storage and eventually onto customers. Next chart. So from a very simplistic point of view, we've broken down the moon into two primary resource aspects. One is the regolith itself, recognizing that over 40% of the regolith has oxygen in it through lots of different minerals. We recognize the two basic differences in the regolith, Mare versus Highland. And since the Artemis program is focused specifically on the South Pole, we are mostly interested in the Highland type materials. We do recognize that there are other potential resources like pyroclastic glasses and the creep elements, rare earth elements, as well as solar wind volatiles, but those take a lower priority. What has gained the most attention from a resource mining perspective is the potential for water. The only true surface impact information we have is from L-Cross, and I have a chart from Tony Colapreet there. Lots of really interesting data as to where that water ice might be and other volatiles and what concentrations they may be found in, but as we all know, there's a lot more to learn. Next chart. So, unlike other folks, we have to embrace and get involved in lunar regolith versus just trying to mitigate it. This chart shows kind of an evolutionary pathway of where we are starting from and where we may go. Small-scale demonstrations and a pilot plant, as I'll discuss later on, look at making tens of kilograms of product to over 1,000-ish kilograms of product. Knowing the different processing rates, for example, one of the oxygen extraction rates typically can extract maybe 10 kilograms of oxygen for every 100 kilograms of regolith. And if water ice is found in 5% concentrations, then basically you can multiply the product value by at least an order or two orders of magnitude to understand how much regolith we need to process. As we go towards trying to refuel descent stages to send back up to orbit for reuse, or even ascent vehicles and reusable vehicles, the amount of product starts growing. And there are commercial estimates that if we had tremendous, lunar exploration and commercial activities, we're talking about, thousands of metric tons of product. And so this kind of gives an idea of again, if you use those multiplication terms, how much material we will be processing over time. Next chart. Construction is another interesting aspect. Phil's last presentation on plume impacts suggests that as we start building up infrastructure, we may want to start thinking about landing pads and berms and other roads for cutting down on the maintenance and wear and tear on our surface mobility aspects and such. During the Constellation program, we started to try to estimate how much material we might want or need to move over periods of time, and it's even significantly higher than some of the production rates that and excavation rates that I mentioned for oxygen and water processing. So that also comes into play. Next chart. So going back to the league strategic knowledge
About 4
gaps,
minutes.
yeah, we have looked at, once again, what do we still need to know? What's still valid from that 2016 report? And these are the aspects that we are using to help drive our prospecting / science needs, as well as our hardware development aspects. It includes primarily what's in the permanently shadowed craters, but there are still, non-PSR related activities associated with understanding the regolith better at the polar locations, and even starting to understand the volatiles that exist outside of permanently shadowed craters. Charging and geotechnical properties, both in and outside the permanently shadowed craters, are also extremely important. There was discussions about adhesion, and that will play into the design of our hardware as well, in terms of our power systems, our thermal control systems, our mechanisms and such. Next chart. So we have a lot of challenges still. We've broken them down into 4 major categories. There's the challenges associated with uncertainties about the resource. Does it exist there? Are there contaminants that exist that we don't necessarily understand? And with respect to Mars, what are the planetary protection requirements? There's been discussion about keeping different parts of the moon pristine as much as possible. So that now may play into how we deal with finding and processing resources, so that we don't have pig pen units churning up dust left and right. There are technical challenges in terms of the energy, life, and performance.
2 minutes.
How dust and regolith degrades our hardware from a maintenance perspective and an operational perspective. There are environmental aspects, the microgravity or the low gravity on the moon, the extreme environments, radiation, low temperatures, the fact that we may not have continuous comm capabilities, surface navigation and such. And then there's integration challenges. Once we have these products, are other systems designed to take those products into consideration and use them? So, how do we clean the water that comes out of a permanently shadowed crater so that we can electrolyze it or have crew drink it, for example? Next chart. And so I'll end my conversation with the fact that we are looking at a lot of these activities from both a ground development perspective as well as a flight perspective. So on the ground development side, we're working on the technologies for both of those pathways, the oxygen extraction from regolith and the water mining, prospecting, and extraction goals. We're initiating surface construction tasks as well. Part of that, as has been brought up, is the development of high fidelity simulants and ground development units. We have started to look into flights. So you may have heard about Prime 1 and Viper. Those are our first steps into understanding the polar resources. At the same time, between 24 and 27, we're looking at flying maybe 2 or 3 demonstrations that will lead to a pilot plant by the end of the decade. I think that's it. Next chart. Okay, I'm done.